And how do we determine this delta VO? We know that the change in charge, the charge that is accumulated on the capacitor when the current is positive. When the current is positive, the capacitor current is positive, it means charge is getting accumulated. So the area under the positive portion of the current waveform is equal to the charge accumulated on the capacitor, and that is how we can write this delta QC, where the delta QC denotes the charge accumulated on the capacitor is equal to C times delta VO. And what is delta QC? Area under the positive portion of the capacitor current waveform, which is half. And what is the base? The base is Ts by 2. Why? Because these are all linear rise and linear fall. The current rise is linear and current fall is also linear. So the duration between this point and this point is exactly Ts by 2. So the base of the triangle becomes Ts by 2, and the height of the triangle is anyway delta IL by 2. So that is the left hand side of the equation, and the right hand side is C times delta VO. So that will give us an expression for delta VO in terms of delta IL, Ts and C. So if you specify a delta IL, we will specify output voltage and switching frequency, we'll get the value of L. Once we know the value of L, we can find the value of C by appropriately specifying the output voltage ripple delta VO, which we want to be as less as possible. And if you want to write the expression for delta VO in terms of VO, because that is what we have been trying to verify. So delta VO divided by VO can be obtained by substituting the expression for delta IL that we derived earlier. So this will turn out to be 1 minus d Ts square divided by 8 LC. So that is what is the ratio of delta VO by VO. So when this ratio is much smaller than 1, our analysis is correct. So we should choose L and C values in such a way that this relation holds good. This relation between delta VO by VO can also be seen in terms of the frequencies. For example, we define the frequency of this LC as 1 by 2 pi root LC, which is known as the corner frequency of this LC filter or resonant frequency of this LC. So if we define FO as 1 by 2 pi root LC, and we already know that FSW is 1 by Ts, the delta VO by VO expression can be rewritten as FO square by FSW square into pi square by 2 into 1 minus d. Since 1 minus d is always less than 1 and pi square by 2 is something like close to 5, we can say that delta VO by VO being much less than 1, or the small ripple approximation of output voltage, is ensured by having a switching frequency FSW which is much larger than the resonant frequency of this LC, which is FO here. We have looked at the output voltage waveform and its average value. Now we will also be interested in the input current waveform, because ideally we want to draw a DC current which is constant, and we want to produce a DC output voltage which is also constant. So if you look at the input current, that means the current drawn from the source, how does it look like? It is nothing but the current flowing through the switch S1. So when S1 is on, that current I in is equal to IL because S2 is off. Otherwise, whenever S1 is off, the current flowing or the current drawn from the source is 0. So that is how the input current looks like. The input current is not a pure DC waveform. It goes all the way from 0 to the peak value of IL, which is the average value VO by R plus delta IL by 2. That is the peak value of input current. So we are not drawing a smooth input current from the DC source in the case of a buck converter. So far we have seen the waveforms in periodic steady state of this buck converter. But how does it start? How do the waveforms start from 0? Because that is what will be the initial condition of any practical circuit. So let us try to see how they reach the steady state values, their steady state values through these simulation results. Here three waveforms are shown. The first waveform is the inductor current waveform, and then the second waveform is the inductor voltage waveform. The third waveform is the capacitor voltage waveform, which is the output voltage waveform. So the inductor current waveform, initially it is 0, and it starts rising. Why? Because the voltage across inductor is also positive, because it is 40 volts. The input voltage is 40 here, it's taken as an example, and the output voltage is almost 0. So V in minus 0, which is 40, that is what is appearing across this inductor. So the inductor current rises to some value, and then in the next cycle the output voltage is again almost close to 0. It has not raised so much because the capacitor is starting to charge. So the inductor voltage is almost 0, otherwise it should have been minus VO. So since the inductor voltage is 0, its current doesn't appreciably rise, but as few cycles pass, it will slowly, the negative voltage that is appearing across the inductor in the 1 minus dTs duration increases like this, and finally it will reach a steady state value, and the inductor current in steady state looks like this, and still the capacitor voltage has not reached steady state. So if we go a little further, we will be able to see the steady state in capacitor voltage also. Remember the peak to peak value of capacitor voltage, this is very less. See, the average voltage is almost 20, because the duty cycle is 50% here. The input voltage is 40 volts, so the output voltage will be 20 volts, and that is what is seen here. It is 20 and then minus 20 for equal durations, and the peak to peak ripple delta VO in output voltage is much smaller than its average value VO. So our small ripple approximation is valid, and in fact the capacitor and inductor are chosen in such a way that the small ripple approximation is valid. The next question is, how do we realize this in practice? Like what switches to use where? How do you choose whether it is a MOSFET or a diode in this particular circuit? For that we need to look at the voltage blocking and current carrying capabilities. That means we need to look at the current flowing through the switches and the voltage across the switches under the different intervals. So in the first interval, when switch S1 is on, the current through the switch IS1 is equal to the current through the inductor IL. That is what is shown here in this waveform. And when the switch is off, S1 is off in the second interval, which is 1 minus dTs, obviously the current through the switch is 0. Again it will be IL in the subsequent interval, and it will continue. And what is the voltage across the switch VS1? When it is on, it is almost 0 or whatever is a small drop, that is shown here. And when it is off, when the switch S1 is off, S2 is on. So look at this second circuit. So VS1 is equal to V in. So that is what is shown here. So switch S1 is blocking the input voltage with this polarity. Now let us look at the switch S2. When S2 is on, see the current direction of S2 defined here. So when S2 is on, the current flowing through S2 is same as the current flowing through inductor. That is what is shown from the second circuit. And when S2 is off, the current flowing through that is 0. So that is how the waveform of S2 can be plotted. And when S2 is off, what is the voltage across that? That is in the first interval. So with the polarity that we have defined for S2, VS2 will be equal to minus V in when S2 is off. So S2 is blocking a negative voltage with this kind of definition. And of course the voltage across S2 is almost 0 when it is on. So if we look at the voltage blocking and current carrying capabilities that are required for switches S1 and S2, when S1 is on, the current through S1, which is IS1, is only positive, and when S1 is off, the voltage across the switch VS1 is again positive with the polarity defined. So we can choose a MOSFET connected like this in place of S1. And how about S2? When S2 is on, IS2 is positive, but VS2 when it is off, when S2 is off, the voltage across the switch VS2 is negative, so naturally a diode becomes a choice. The resulting circuit for a buck converter realized using practical switches is shown here. It has one fully controlled switch, which is MOSFET, and one uncontrolled switch, diode. So as soon as the MOSFET is turned off, automatically the diode takes over the current. And this MOSFET can also be replaced by an IGBT. The S1 MOSFET can be replaced by an IGBT with collector and emitter terminals properly connected. That is done at higher power levels. Alternatively, one can also use a MOSFET in the place of S2 as shown here in reverse direction. This is taking the advantage of the fact that MOSFET channel, the channel in a MOSFET can conduct in both directions. So the terminals X2, Y2, between the terminals X2, Y2, the MOSFET can be connected with source at X2 and drain at Y2. Such a configuration is popularly known as synchronous buck converter. The operation of synchronous buck converter is the same, except that we need to take care that S2 conducts, or S2 is given a gate pulse, gate voltage is applied on S2 as soon as S1 is turned off. How do we incorporate the effect of non-idealities like resistance of the inductor or the voltage drop across a switch when it is on, or ESR of capacitor in the analysis of DC-DC converter? Let us try to understand through an example. Let us consider this buck converter circuit, and we want to look at the effect of the resistance of an inductor, including the resistance of an inductor, on the voltage gain. What do you mean by voltage gain? It is the ratio of average output voltage to the input voltage. So we'll just start include that in the circuit. RL is shown here, and when S is on, S1 is on, we have the circuit, a similar circuit, but then with RL as an additional element, and that will appear as a separate term in the KVL, like minus RLIL. So voltage across inductor will now be V in minus ILRL minus VO. That is how the KVL gets modified. And in the off state of S1, that means when S2 is on, then also the voltage across inductor can be expressed as minus VO minus RLIL. That is again this drop coming into picture. And we have already applied the small ripple approximation, where the output voltage VO is assumed to be smooth, or the capacitor is large enough to make sure that that approximation is valid. So now we have an expression for the voltage across inductor for DTS and the voltage across inductor for the remaining 1 minus DTS. And in periodic steady state, we know that the average voltage across inductor is 0. So we just do this integral 1 by Ts, integral 0 to Ts, VL dt is 0. So this integral needs to be split into two parts, because 0 to DTS VL has one expression, and DTS to TS VL has another expression. And if you plug in the expressions and do the integral, we can show that it is d times V in and RL IL and minus VO is equal to 0. And what is this IL? Capital IL. Capital IL is the average current. It is basically 1 by Ts integral 0 to Ts IL dt. That is the average value of inductor current. So that comes in here, and that is nothing but VO by R, as we have seen earlier. So if you plug in the value of IL into this expression, what we get is VO is equal to dV in divided by 1 plus RL by R. If RL is 0, the output voltage is just dV in, that's the ideal condition, but in reality inductor will also have some resistance, so the voltage gain will be less than expected. So you will be expecting some voltage like this at a given value of duty ratio, but then the actual voltage might be little less than that. And how much less? It can be found by following this method. So if you plot VO by V in, the ratio of the average output voltage to the input voltage against D versus D, you will have a series of straight lines, and each straight line corresponds to one condition of RL by R. And as the RL by R increases, that means when RL becomes more and more significant, then your output voltage also becomes very low, much lower than the expected value. In the same fashion, we can also incorporate the voltage drop across switch. For example, this is VS1, voltage across the switch when it is on, which is non-zero, so that can be incorporated. Similarly, the voltage drop across S2 can be incorporated. So, and ESR of capacitance also can be incorporated. The voltage drop across ESR can be incorporated. So all these non-idealities will amount to a lower voltage than the expected ideal voltage. So we need to choose components in such a way that these non-idealities do not affect much and we get the desired output voltage which is close to the ideal case.